there's no other questions from homework, everybody has the sheet, I'm assuming. Okay. So yesterday we managed to, okay, what's happening? Boom, boom, boom. Okay, okay. Oh, that's as close as I'm gonna get. That's too bad, Jeff. Let's turn it off and turn it back on. It won't turn on. Oh my gosh, the machines have taken over. This is interesting. So take away your power. There we go. Aha. All right, let's try this again. All right, little dude. Oh, he didn't like that at all. Shit. Okay. He's thinking. Okay. I'm so happy I'm getting this recorded. Okay. Let's see if this works. So we got into polar coordinates. All right, are you gonna work this time? No. Oh, look at that. I never saw that before. Okay, sorry. Easily distracted, I am. All right, so we got this far yesterday. So if you weren't here yesterday, I highly recommend you watch that video. So basically, the idea is, let's say this room has an XY axis. So I'm right at the origin, right? You guys are all sitting off the side. So the y-axis goes right there. You with me? So if I want to get to Riley, I have to go 1, 2, 3, 4, 5, and then 1 over, right? Okay, so I can find all of you by walking up and then out. That's Y and X, right? Alternately, if I wanted to go to Riley, I could just say, all right, turn this much by this angle, and then walk this far, right? So I could either use X, Y to get somewhere, or I could use turn, walk this far. Because what's the XY axis? What's the XY coordinate plane for locating positions in 2D space, right? Is that the only way to locate a position? No. So I can ask somebody to, let me see. So we talked all about this yesterday, but it's important to really re-emphasize why we do weird shit as math people. Paper. Papier. What are you, paper? Your paper. Okay. So I could either locate this point by walking over on the X and then up on the Y. Bam. Or I could tell somebody who's standing here, turn this far and then walk this far. So that's polar. That's polar coordinates. It's just another way to locate a point. You with me? Okay. If you've ever given directions to somebody, are there multiple ways to give directions to that person? Yes. You could say, turn left on Elm Street and then turn right. Or you can say, remember that old jacked up house that got hit by lightning? Yeah, turn left there. And then, right? No? Yes? Okay. So, what that leads to, if I bring this back, very obvious correlations between these x squared plus y squared equals r squared. Cosine theta is x over r, so x equals r cosine theta, so forth. I've got a beautiful right triangle, nothing amazing there really. So that's where these guys in red come from. I like it. That's something to make this work. Hey, that's not too bad. Okay. All right, how you guys all doing so far? I know a few of you guys weren't here yesterday. Please go watch the video. That is my catch-up lecture right there. Okay, let's jump back into this. we left off, we sort of talked about this one. And just to make sure you understand what I was saying about finding theta, let me get a clean guy to work on. Okay. If I wanted to find theta, what should I use up here? If I have this problem right now, do I know what R is at the moment? What's the only thing I know given this point? What system is this in, this point?
X and Y.
Good, XY, rectangular, but XY. So the only thing I know is X and Y. It's all I freaking know. Is there something in red that is actually still showing right now that relates XY and the angle? Is there anything up here that relates the angle?
Theta.
Yeah, tangent theta equals y over x, right? So if I say tangent theta equals y over x, what is square root of 2 over 2 divided by negative square root of 2 over 2? What is something divided by negative itself?
1.
Negative 1, right? The negative is still there. Okay. All right. Let me stop for a moment, make sure everybody's with me. So yes, the stuff in red you need to memorize. The funny thing is, don't you already have tangent theta equals y over x? Isn't that memorized? It's nothing new there. X squared plus y squared equals r squared. That's Pythagorean theorem in a circle. Whoop-de-doo, right? Cosine theta is x over r. Sine theta is y over r. That's what those are, right? All of those things you have memorized. We just haven't used it the way we're doing right now. So none of this is new. The way we're using it is new, for damn sure. Okay. So you have to memorize those. The great thing is you should already have them memorized. Unless you don't, in which case that's a bad thing. Can anyone tell me where tangent is negative 1? We kind of did this one last time a different way, but I figured I'll do it this way this time. Say it.
On the y-axis.
No, careful. Tangent is sine over cosine. So basically, what's the only way that, if tangent is sine divided by cosine, what's the only way it can equal 1? If sine and cosine are, what's the only way I could divide two things and get 1? If they're equal. Where's sine equal cosine? What angles? 45 degrees, right? Pi over 4. Are you guys with me? Do you guys see the way you have to think when you're given a little mini equation like that? What angle leads to okay, at 45 degrees, but what quadrants do I have to be in for it to be negative? Which quadrants make tangent negative?
2 and 4.
2 and 4, because that's where y and x are different signs. Is everybody with me so far? Which quadrant is this in? Negative x, positive y. Second quadrant. So what did we just figure out? The only tangent can be 1 is at a 45 or pi over 4. I must be in the second quadrant. So what's the pi over 4 reference angle in the second quadrant? Second? 3 pi over 4. Bam! If you throw that shit in your calculator, do the inverse tangent negative 1, it's going to give you a decimal. Do you think I want to see that? I don't want to see that shit. This is something you should be able to do. So theta is 3 pi over 4. I really want you to notice, by me just giving you a point, I have told you what quadrant you're in, right? You can just imagine if it's positive x, positive y, first quadrant. Negative x positive second quadrant, so forth, right? You know what quadrant you're in. Okay. How do I get, what's the other thing I need to make full polar? Go full polar. R, all right? Polar is r theta. So r is going to be relatively easy, yes? R squared is? x squared plus y squared, right? So now you just have to square that and square that. What is rad 2 squared? 2. What's 2 squared? So this is 2/4, right? The negative cancels. 2/4 plus 2/4. 4/4 is 1. Why am I, and so r squared is 1, so r is 1. Nobody should be surprised by that. If the x piece is rad 2 over 2 and the y piece is rad 2 over 2, we must be in the unit circle. Right? Aren't those unit circle values? So r being 1, we totally knew that already from the beginning. Let me stop for a minute. So if I have two ways to locate a point, there must be a way to kind of convert from one of those ways to the other, right? If I said to somebody, yeah, remember that jacked up house got hit by lightning? Turn left, and like, I don't remember that. All right, a different way to tell you is that's Elm Street, turn left on Elm Street. Oh shit, I got you, right? I chose a different way to explain to somebody how to get somewhere. And I have a way to convert between one and the other. Okay, maybe. So here, I want to convert the given equations to polar. So last time we did these, and just to remind you real quick, if I see a sine theta, it's related to y. I'm just missing an r here. So if I multiply both sides by r sine theta is y, and r squared is x squared plus y squared. So the whole idea is to make something up here show up. So then I can just replace it. So here, this is really nice. Do I know y in terms of r and theta? What is y in terms of r and theta? R sine theta. So I can just put r sine theta. And what's x? R cosine theta. So then if I wanted to, I can multiply that up and I get this. Oops, sorry, down here. All right, so y is r sine theta, x is r cosine theta. Is there any x or y left right now? Right here, is there any x or y left right here? Nope, I replaced all the x and y stuff with r theta stuff. So did I get away from rectangular fully to polar? Yes. Anything after that is just kind of cleaning it up a little bit, so I can multiply that up. I mean, that looks like a nice little equation. Let me see if anybody notices this. Does anyone see a trig identity in there? If there was a 2 next to the r squared, you would have 2 sine theta cosine theta, right? What is that? Sine 2 theta. So I don't have a 2, do I? So this must be 1/2 sine 2 theta. Now if you didn't notice that, don't worry, please, right? But if they were trying to say, show that this is this, you would have to go that extra step, right? But if I just said this, you could stop right here. That's why I boxed it off. Or you can realize you can go one step further, make it a little bit of a smaller equation. Are you guys okay with that? Maybe. That's half of what it needs to be sine 2 theta. Okay. God, I need to learn how to give enough room on these things. All right. Someday. So look at part B. There's a few different ways to do part B. I could just replace x and y with r cosine theta, r sine theta, right? Or I could kind of multiply this out a little bit. So let me show you what. So do you guys see I could just put r cosine theta there and r sine theta there? And then I still have to multiply this out. So let's just go ahead and multiply it out first. Let's see what we get. X squared plus, this is relatively easy, y squared minus 4y plus 4 equals 1. Well, what's x squared plus y squared? In terms of polar stuff. R squared. What's y? R sine theta. And let me go ahead and subtract the 1 over. That looks like a nice equation right there. Look at that. That'll be the mathematical Bob Ross. Look at that nice little equation that lives right there. Gotta work on my hair. Okay. All right. Now with that in mind, so there you could have from the very beginning put r cosine theta, r sine theta right there, but this was a little bit better to first multiply out. With that in mind, can anyone see a really good first step on part C? Yeah, if I add y squared to both sides, well, what's x squared plus y squared? R squared, and what's y over x? Look up at the top. What's y over x? Say again? No, come on, you're better. Tangent theta. If you do that, it would eventually become tangent, right? The r's would cancel. Sine over cosine is tangent. Bam, look at that. Bam. Okay, maybe. Yes. Oh, did we? Yeah, let's do that real quick. So this is, if I'm trying to convert two polar, this must be x, this must be y. And the polar coordinates are r theta. So how do I get r if I know x and y? I got this here, right? R squared is x squared plus y squared, so I do r squared is square root of 3 squared plus 1 squared. R squared is 3 plus 1, 4. So r is 2. And then how do I get theta? There's sort of two ways, but there's one that's better. Which one directly relates theta with x and y? Directly, not two different ways. Here, right? So then theta would be inverse tangent of y over x. One little thing about tangent, I don't know if anybody has noticed this. Is it cool? I can do the same thing to the top and bottom of a fraction, right? Hello? Sorry. Hello? Yes. I could do the same thing to the top and bottom of any fraction. I can multiply, I can divide, correct? So look what happens if I take this fraction and I divide the top and bottom by 2. You're like, okay, Jeff, but didn't I just make certain values show up? Isn't tangent sine over cosine? When is sine 1/2 and cosine is rad 3 over 2? Pi over 6. So theta must be pi over 6. So what's the point? Yeah, Jeff, what's the point? It'll be 2 pi over 6. And real quick, how do I know that's pi over 6 is the right angle? Well, what quadrant is this point in? First quadrant, because x is positive, y is positive, right? So therefore, pi over 6 is not a reference angle, it's the actual angle. Okay, maybe. Yes?
So why did you divide by the top and half?
Just to show you another way to think about tangent, when I see rad 3, or 1 over rad 3, those are tangents that I should know. I shouldn't have to put that in the calculator. I should just know. Here's what I remember, right? Tangent is smaller when sine is smaller because sine is on the top. Tangent's bigger when sine is bigger because sine's on the top. So when I see 1 divided by rad 3, that's pi over 6, because that's where sine is smaller. When I see rad 3, if I said the inverse tangent of rad 3, that's bigger. That must be pi over 3. So that's how I memorize things. But I just want to show you how to make the values we know. 1/2, rad 3 over 2. I can make those show up. You don't have to. You never have to do that, ever. But I just want to show you could. Okay. We did a few of these, but real quick. Let's do this again. Can somebody tell me what instructions part A gives me? Because, for example, if I said plot the point 1, 2, what directions does this give me? It tells me to do what? Go right 1, up 2. So it gives you directions, correct? That's what a point does. So what directions is this point giving me right here? What way should I face? Turn by how much? Pi over 3. Turn by pi over 3. So I'm going to be looking at pi over 3. And how far out am I going to go?
Up 3.
Well, I'm going to go out 3. 1, 2, 3. So that is the point 3 pi over 3. We just have to, x, y just tells me how to move left and right, up and down. R theta tells me what angle to turn through and then how far out to walk. That's it. We don't even think twice about x, y anymore, but it's telling me directions. This is just telling me directions, just in a different way. Okay. So real quick. If I wanted my friend to get to my house, and they live here, and I live, well, let's see, they live here, and I live there. I could either tell them, go over this many blocks, and then down so many blocks, right? X, Y. Or they got the private jet, or the helicopter, and I'm like, okay, get on the top of your house, turn by this angle here, and then fly this far. Now that's why most of us don't have a private jet or a helicopter, right? Does anyone have that? That's why this is most often used in boating, because the ocean, I could go most of the time any freaking direction I want to and just go, unless there's like rocks or an island or whatever, or another boat. Yes? Maybe? Okay. Can't really do as the crow flies on land, because we're not crows, so we have to follow the roads. But in the ocean, go whatever direction you want to. Maybe. So this guy, where do I face? So I'm at the origin. Which way do I face? I look at this guy, and then I go forward. 1, 2, 3, 4. That's B. So can somebody point out to me, where is the R-axis? Right, we have an x-axis and we have a y-axis. Where's the r-axis? Oh, shit.
Inside?
What shape does the r-axis take on as you move out?
Circle?
The circles. The circles are the r-axis, right? And the angle axis are the lines going out, right? Okay, very funkadelic. Maybe. 3.5 pi, so I face pi, and I go out 1, 2, 3.5. Right? Do part D. face pi over 6. So I'm facing that way. And I'm going to go out 1.5. So that's D. So like I said yesterday, in your homework, please, dear God, label your points. Right? If you just give me this big thing with just dots. Oh my God. And I don't think I've done this yet, but I need to post, I'm going to post blank sheet of this graph paper. So you just print it out, right? If you need to, I can print it out for you in my office. You guys with me? Or you just get polar graph paper. This is the best I found yet. This is really nice. I like this polar graph. It breaks it down by 12ths in case you need it. Okay. What about E? Does somebody remember how to do E? E's a little different.
Go backward.
Yeah, I'm going to go backwards eventually. So I face 2 pi over 3. And then I go back 1, 2, 3. So I look this way, but I walk backwards 3. Could somebody please tell me another way to identify that point with a positive 3? Yeah. Face 5 pi over 3 and go forward 3, right? Cool. Okay, maybe. And then what about this guy? The difference here is, where's negative 11 pi over 12? It's not here, right? Where's negative 11 pi over 12?
13 pi over 2.
Yes, 13 pi over 12. So I go back 11 pi over 12, I'm going to stop here. It's pi over 12 short of a full pi, right? So I face this and I go forward 1, 2. Does every circle always have to represent 1? No, it's a scale. I can make it different. I can make my R scale go by 2s. I can make it go by 7s. I can make it go by 0.5s. Of course I can. Just like with X and Y axis. How do you guys feel about that, yes?
Can you repeat S, please?
Which one?
Last one?
Okay, so where is a negative 11 pi over 12? So I'm going to go back, right? Negative 11 pi over 12, so I'm going this way. So negative angles. And I'm just short of a full pi, right? I'm pi over 12 short of negative pi. So of course I'm going to stop here. That's pi over 12 short of a full pi, right? So I'm going to face this. I'm going to go forward 2. So what's another name for the point in part F?
13 pi over 2.
Yes. What's another name for the point using negative 2? What's another name for this point here? Well, when I go back to, I must be facing where?
Pi over 12.
Pi over 12. There we go. So again, the funky thing about trig and unit circle is any given place has an infinite number of ways to describe it. And we're seeing that here. So there are an infinite number of ways to describe any point in the polar coordinates, which sort of sucks. Okay. By the way, real quick, I want you to understand why this makes some sense. So if I'm in 2 dimensions and I go here and then I rotate again, I go here, I'm still in the same spot, aren't I? Have you guys ever been in a parking garage where you go down and it's this spiral thing and it's got like you can shoot off to go on each level? Have you guys ever seen that or been on that? So if I'm in there, if I go up and I make a full rotation, aren't I at a different location? I'm directly above the other point, aren't I? That's, when I bring 3 dimensions in, that's why now the rotation makes beautiful sense. I am in a different place, not this way, but this way, right? So if I add a 3rd dimension, when I rotate a full rotation, the circle thinks I'm in the same place, But the reality says, no, you're up. And then I do another rotation. Now I'm further up, right? I don't know if you guys understand what I'm trying to say. So when I'm 2D, this is really stupid. I'm there. Well, what if you go 80 times around and then I'm still there? You know, you're like, that's great, Jeff. But once you add another dimension, now it makes sense. You can actually identify places up and down. Okay, maybe? Okay. Okay. So, major announcement. Oh shit, sorry. I'm gonna post this. You'll notice a few more blue things here, possibly. Let me zoom in a bit. So, yeah. The end is near, so I'm really having to be very specific with what's most important. So I have decided to make 10-4 extra credit. I think that's new. Can't remember now. I think that wasn't extra credit before. Oh, I had them somewhere. It doesn't matter, Jeff. You guys see this? So 10-4 is extra credit. 10-5 is extra credit. 10-8 is extra credit. I think these were already extra credit. 11-4, 11-7. And I had put to be announced because it depended on if we had enough time. And we definitely don't. So I'm gonna throw sequences out. Right? I'm really sorry if anybody was looking forward to sequences, but we're just gonna throw them out. We are gonna still somehow do this. I'm working, look, can you see where my cursor is? I'm working on cutting these sections, assignments down. All right, is that okay if I do that? I love you. You're like, yes, do that. So I'm gonna probably cut some of the homework down for some future sections, just because I'm aware finals are approaching, your other classes have, like, normally at the end of the semester, everybody suddenly has these major assignments due. Is that true? All right, so I'm gonna try to cut the homework back a little bit. Like 11-2 is already barely there, so I'm gonna leave that guy alone. But anyway, okay, you guys all with me? So I'll bring hard copies of this tomorrow and I'll post it up on Canvas. Okay, maybe. So what we just did today, if I remember correctly, was 10-3 should be, okay. 10-3 is polar coordinates, yes. What we're not gonna do in 10-4, real quick, I wanna talk about 10-4 a little bit. What we're not gonna do in 10-4 is talk about graphing polar equations, which is kind of unfortunate. So I really want to quickly show you something nifty. Here, does anyone need to borrow a calculator real quick? I want you guys to have this experience. If you want a calculator, you need one, let me know. Anybody? Is it really cool? Okay. All right. I finally, by the way, I've been trying to get this program this whole semester, and they said, oh yeah, we'll do that when we're gonna update the computer, we'll do it. And they finally updated the computer. Make sure it turns on. Anyway, so watch this, this is so cool. So everybody, if you hit your Y equals button, does everyone have this kind of thing show up? Right? All right, right? Nothing amazing, we've seen this before, whoop-de-doo, right? Go to mode, right here. And do you see down here where it says function? Do you see something else in this list that's familiar?
Polar.
All right, sweet. Let's go to polar. Oops, shit. Polar, enter. Now when I hit Y equals, it's actually going to say R equals. Now let's try something. Everybody try this. Do sine. Now watch this. This is cool. When I hit my all-purpose variable button, it's now theta. Of course it's theta, because now we're in polar coordinates, right? So let's try to graph this. Can everybody do zoom 6? everybody should get this tiny little circle. Let's kind of blow that up. If I go to y equals again, let's clear this. Let's make it 5 sine theta. Let's blow it up a little bit, right? Let me know if anything weird happens. 5 sine theta. Now it should be a little bigger. Does that look like a circle?
No.
No, right? It looks like Stewie's head. It looks like an ellipse. It looks like an egg. That is a circle. It is. It's just on a rectangular. It's not your window is not square. Do you guys see that? So it's been squished. So it's unfortunate that the way they made these TIs, everything gets squished. So every graph you've ever seen is actually a little off from what it should be because it's been squished. Maybe? Is that cool? Okay. I think, real quick, I think if I make, I can't remember now. Yes, I think if I make x min 16 and x max 16, does that, then it looks more like a circle, right? No? It looks more like a circle, doesn't it? All right, maybe you guys. So I'm going to do zoom 6 and come back. Now, real quick, let me ask you this. Where's the center of that circle? On what axis? Y-axis. Which trig function likes y? Sine. Which trig function did we use in the equation?
Sine.
Holy shit. What's going to happen if I make that cosine? What do you think? It's going to be on the x-axis. Crazy, right? Okay, maybe. And by the way, real quick, when theta is 0, what's cosine? What's cosine of 0? What's cosine of 0? What is cosine like? X. What's cosine of 0?
1.
1. Okay, good. All right. I'm not asking you to convert an angle to radians, and I'm saying what is cosine? What's the biggest cosine can be? 1. So the smallest cosine can be? -1, right? Okay. So at 0 degrees, I get 5 times 1. So sure enough, look, isn't this 0 degrees? At 0 degrees, I get 5 times 1. See how it's at 5 right there? When I make the angle get bigger, isn't the answer smaller? That's why it starts to come closer and closer to the origin. What is it at 90 degrees? A pi over 2. What's cosine? 0. So when I'm at 90 degrees, it plots a point at 0. Maybe. Now watch this. What if I do something like, no. What if I insert a 3? What have I just changed? What does that do to the cosine graph when I put a 3 in front of theta? That's what we call k. Do you guys remember? What does that change? Period. So that's really not going to do much except for this. Now that is funkadelic, right? How many leaves does that have? 3. So what do you think is going to happen if I make this 7? Now, that looks really bad, doesn't it? Now watch this real quick. I'm spending too much time on this, but I just want to show you. If you go to window, do you see where it says theta step? If I make that smaller, it's going to step through my theta's smaller steps. So it should make the graph, see how it's more rounded? So what do you think is going to happen if I put a 4 here? Let's see. Oh, what the shit? How many leaves are there now? 8. Weird. So when it's odd, it's that many. When it's even, it's twice. So there's a whole shitload of things that we could discuss in that section. There just isn't time, but I want to at least show you some stuff. So maybe you'll start playing around with it. Real quick, watch what happens if I do something like this. Plus sine of 2 theta. You get some funky stuff happening, see that? It's a little, it's not as symmetric as it was before. All right, so what if I make this odd, nifty? I don't know if you guys are doing okay up there. What if I make this sine squared? I'll stop playing after this. Nifty. All right, I'll stop. What if I make it theta plus sine theta? Nifty. Anyway, I'll stop. Okay. Hold on to those calculators, by the way. We're going to use them again in a minute. But I just wanted to at least show you enough that maybe you can go in there and just start playing around with it a little bit just to see what kind of happens. There is, remember on Canvas how I have a butterfly? I'm not going to do it right now, but I mean, I'll look up the equation and I'll program it in the computer yet tomorrow so you can see it. There's an equation that will create a butterfly on your calculator. It's kind of nifty. It's like, all right, that's not, normally I don't associate math with butterflies, but why not, right? Okay, enough. So, you were done with that? Okay, good. So, coming back to this real quick, just to remind you, 10.4 is extra credit. That's related to what we were just doing. 10.5 is extra credit, which was, let's see, what was that? Where are you at, 10.5? Probably after 10.4. Oh yeah. All right, so this one is kind of unfortunate that we don't have enough time for this, but what do you guys, just looking at the title, are you upset that we're not doing this? I am upset we're not doing this. I am very upset we're not doing this, but so I highly recommend, if you're interested in mathematics and you're going much further in math, you should probably do this. The reason I can kind of let this one go for us is if you go further in mathematics and you get to a point where you need this, they're going to review it as if you've never seen it anyway. Just to be careful, right? But it's here. And it's nifty as frickin' hell. And I'm sad. But it's okay. I'll be fine. It's my fault, so it's okay. All right. So the next section we actually have to do is section 10.6. And oh, that's neat. 10.6 has to do with an entirely different way, to find points in a grid, right? So let me ask you this, okay. Just to remind you something, I'm going to post blank polar graph paper, because in the homework that you have to do, you have to plot polar graph points. And if you try to do it on your notebook paper, it is going to suck, because you're going to try to find and estimate angles. No. Get some polar graph paper, please. Okay. And again, it's not that hard. You just have to get practice with it. It's a different way of thinking about things, but it isn't that difficult to do. You just have to get practice. Let me ask you this. Let me just say this. Etch-a-sketch. Etch-a-sketch. Has anyone ever heard of Etch-a-sketch? Anyone never heard of Etch-a-sketch? All right, it's okay. It's this orange thing that with knobs. Let me show you what it looked like. Bum, bam. Right? Isn't that Etch-a-sketch? What the hell am I drinking? Maybe I need more of it. Whoa, okay. So these knobs, when you turn them, there's a little, it's actually like a magnetic thing, a little stylus that's poking the screen. And when you turn the knobs, the stylus moves. One knob is the x-axis, the other knob is the y-axis. And as a kid, you didn't freaking think x-axis, y-axis, right? So watch this. So if I turn one of the knobs that goes left and right, whee! If I turn the other knob, it goes up and down. Whee! Right? If I turn both knobs at the same time, what will happen? No. It's not going to go in a circle. If I turn both knobs at the same time at the same rate,
A line?
it's going to make what kind of line? I just made lines. What kind of line? If one knob moves in the x direction and the other knob moves in the y direction, when I turn both of them, it should move. Well, let's find out. I'm going to turn both knobs. You ready? Well, let me shake it. Isn't that crazy? All right, just like. All right. This works exactly like. So watch it. I'm going to hit both knobs. Of course, it goes at a diagonal, right? It wants to move in the x and the y direction, so of course it's going to move at a diagonal. What if I turned one knob faster than the other one? What would happen to that line? It won't curve still. If I turn one knob twice as fast as the other one, it'll go at a different angle, right? If I turn both knobs at the same speed, it goes perfectly 45 degrees. If I turn the Y knob a little faster, it's going to go up faster. If I turn the X knob faster, it's going to go over faster. Are you guys kind of with me? Isn't everything happening that I'm doing, isn't it all in an XY plane? Isn't that just an XY plane? You guys, it's 2D, so it's an XY plane. Is Y changing because of X? Do I only turn one knob to make everything happen? No, I'm turning two knobs, right? So we normally think of Y as a function of X. What makes Y change is if I change X, correct? Look what we got. We have an XY plane. Is Y a function of X? No, I could totally turn each knob in different ways. I'm not gonna do that one. You know, I could just turn them at different speeds. I could turn them at different times. Are you guys with me? I really want this to make sense. So, what this means is there is a third variable controlling both X and Y. And what is that third variable? Me! I'm the third variable. I can control X and Y, each of them separately. I can control them myself. I don't let X control Y. Every function you've ever looked at, X has controlled Y. Does that make sense? You make X 7, and then Y is 3. You make X 8, and Y is 12, right? I mean, that's been the whole thing we've been doing the entire damn time, correct? We're finally going to break that up. Okay. So, Jeff, this is great. Are we all going to get Etch-a-Sketches? And that's going to be part of our assignment, is to come up and show you the Mona Lisa. Right? Has anybody ever seen people that can do that? I suck with Etch-a-Sketch. If I make a nice box, I'm like, I've achieved something. All right. So, what does this look like mathematically? Jeff, okay. So what we're going to get, oh shit, is something like this. This is called parametric equations. Have any of you guys ever heard, holy shit, y'all know that says equations. Have you guys ever heard the word parameter? The parameters of the situation. Parameter is another, sort of another name for variable, but it's different. So let me show you. If I said x is 2t and y is 3t. T is our standard parametric variable. Just like x and y are our standard rectangular coordinate system variables, right? As I change t, don't x and y both change? Which one is changing faster?
Y.
Y. It's changing 3 times every time t's changed versus 2. So it's 1.5 times as fast changing as x is. So if I do this on the Etch-a-Sketch, it should be a steeper line because it's going up faster than it's going over. Is that cool? Y is changing faster, so it's going up faster than it's going over, so it must be a steeper line it would make. Let's make some points. How the hell do I make points? Normally we do this, correct? Because x is the input, y is the output. Now, what's the input? T. And the output is both x and y. So let me do this like this. You're going to see a lot of problems that tell you what t can be. Okay, so let's go from -2 to 1. -2, -1, 0, 1. When t is -2, what is x? -4. What's y? -6. When t is -1, -2. -3. When t is 0, 0, 0. When t is 1, 2, 3. Okay, I like it. So real quick, when I did the Etch-a-Sketch, I was t. I was changing how I was turning the knobs, correct? So I was t. Do I show up on the finished result on the screen of the Etch-a-Sketch? When I do it, am I in the Etch-a-Sketch going, hey? Am I there? No. T is behind the scenes, right? It's that cabal that we all know that runs the whore. No. So t is behind the scenes causing both x and y. So what do I plot then? I'm going to plot this. T doesn't show up. I always do this for myself so that my brain sees this correctly. We've just created 4 points, right? Let's plot those points. Let's see. My beautiful scale, good Lord. So I want -4, -6, -2, -3, 0, 0, and 2, 3. So I get this nice straight line. Kind of a boring first example, but I just want us to get the idea. What's the slope of this line? It goes up. How much? Up. It goes up 3 over 2. Slope is 3/2. So it does go up faster than it goes over, correct? How do I, in polar, can't I convert between polar and rectangular? That's a huge thing we just did, right? So I want to convert from parametric back to rectangular. I want to get rid of t. How can I get rid of the t? Say again? I pick one of the 2 equations and I solve for t. That's one way I can do this. So let me pick the first one. How do I solve this first one for t? Like you said, I divide. So I get t is x over 2. So wherever I see t, I can put this, correct? So I can put that right there. Whoops. Isn't that basically what we just said? Isn't this a line that has a 3/2 slope? And it goes through the origin, so that's not a surprise. And again, this is a pretty boring example. This is me just doing this. It's turning the y knob faster than the x knob. It's just going to make this boring diagonal line. Ooh, Jeff. Okay. So let's do something a little less boring. Let's see. Yeah. Let's do, this is 1. Let's do 2. X equals, what do you got, Jeff? T squared. And y equals, What do you got, Jeff? What do you got, buddy? You can do it. 1 minus t cubed. Yeah, that's funkadelic. All right. So do you understand how I could be given x and y as any function of t in the whole universe? What's really, really funky here, what I don't think any of you are realizing is the results are xy points I can graph. But now, there's a lot more freedom for them to do almost anything they want to do. Because x doesn't care what y is doing really, they're just both functions of t to begin with. So it can just do all this crazy shit that it didn't used to be able to do. So let's see what happens. Let's make a, and let me say that t goes from, let's go from -2 to 2. There's another way you can see that. T is in -2 to Jeff. That's awesome, Jeff. There you go, buddy. So let's make a table of values and see what this weird ass thing does. All right, so -2, -1, 0, 1, 2. Right? So my normal XY table just becomes one column bigger. But it's still creating points. So when t is -2, what's x? 4. And what's y? No. Y will be 1 minus -2 cubed. -2 cubed is -8. 1 minus -8. 1 plus 8, 9. -1, x is 1. -1, 1 minus -1, 1 plus 1, 2. Is everybody with me? T is 0, that's 1. When t is 1, that's 1, and that's 0. When t is 2, that's 4. And this would be 1 minus 8, right? -7. Okay, let's see what this thing looks like. Yeah, Jeff. Okay, 1, 2, 3, 4. So let me do this for myself. I do this so my brain sees this correctly. You see, I don't want t to kind of creep in there and do shit. Stop it, t. I need to be able to go up to 9. Let's see. Let's do 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. This is 1, 2, 3, 4. So as always, I want to pick a good scale and so forth. So at 4, it goes 4, 9. Oh, I forgot to do one thing. We'll do it now. 4, 9. 1, 2. 0, 1. 1, 0. 4, -7. So it goes, now watch this. This was the first point I did, correct? Right? So it goes like this. Does anyone see what this kind of looks like? Especially if I could draw better. That'd be great. Oh boy, this is funky. My scale is really bad, but oh, no, stop. You don't exist there. This shouldn't be straight lines, but my scale just really sucks. But look what I can do. I could put a direction of travel in here. This is the direction it's going. It shouldn't be a V. Dadgummit. My scale just sucks bad. Let me see. It should be like this. But my scale just really sucks bad. Oh. But I give it direction. It's moving in that direction. So what would be good to use parametric equations for? What about comets? Am I not interested what direction a comet is going? Right? If I see a comet, isn't it totally different if it's coming for us or if it's moving away from us? Yes, that is very different situations. So if you use parametric equations, you can build into it a direction of motion. If I just have y equals 2x, it doesn't give a shit. what way you go on it. You can go either way you want to. Does everybody see that? So like the t, the reason we give that the variable, we made the variable t is because very often it's considered to be something equivalent to time. So as time moves forward, where is this thing? That's one big thing we use parametric equations for. Okay, let me give you this funky thing.
So does T allow X and Y to become independent?
Since they're both dependent on t, I can find a relationship between x and y. So real quick, on this last one we did, this one is, let's see. This one's a little bit tougher, but can you imagine a way to solve for t, to get x and y, how do I say this, to be the same thing? So let me show you something kind of funky. This is a semi-difficult problem. Sort of not really, but actually it is. So watch this. T squared is x, correct? And t cubed is 1 minus y. Is that okay if I solve? So let's see. See if you guys are cool with this. If t squared is x, that means that x, let's see if you guys are cool with this. T squared, if I raise both sides to the 3/2 power, oh shit, I get t cubed as x to the 3/2 power. Okay, that's a little weird. But then do you see how t cubed is 1 minus y and t cubed is x? So isn't 1 minus y equal to x to the 3/2? So getting rid of the letter t, getting rid of it, is sometimes a little tricky. That's one example where it's a little bit tricky. Okay. I could just take a square root here and plug it in, but I just want to show you a different way to do it. Now, looking at this, just to show you how you are not going to get away from trig anytime. It's always going to show up now, whenever it wants to. Let me see if you guys can go ahead and try to fill out this table. Do you guys see what t does, right? -4 to 4? Try to fill out this table. So we got -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay, let's see. That trig function shouldn't be that scary because as you put in different values of t, it's going to just come out to be different multiples of pi over 2, which is nice for sine, right? So when you put a negative 4 in, don't you get on the inside negative 2 pi? What's sine of negative 2 pi? 0, because negative 2 pi, I'm back on the x-axis. Sine hates it there. 0. When you put a negative 4 in here, what do you get? Negative 4 squared is 16. 1/2 of 16 is 8. 8 minus 4, I get 4. Is that cool? So every even number, do you guys see how x is going to be 0? Because you're going to end up with some kind of pi. Do you guys see that? So I know every single one of these, sine is going to be 0 there. So negative 3. So that's sine of negative 3 pi over 2. What is sine of negative 3 pi over 2? Where is negative 3 pi over 2? You guys can do it. If I go back, so 3 pi over 2 is here, right? But if I go back 3 pi over 2, don't I end up at pi over 2? And what's sine of pi over 2? What's sine of pi over 2? 1. 1 times 4? 4. If I put a negative 3 in here, I get 1/2 of 9 minus 4. 1/2 of 9 is 4.5. Minus 4 is 0.5. And you keep going. 1/2 of 4 is 2 minus 4 is negative 2. What is sine of negative pi over 2? Negative 1. Negative 1 times 4 is negative 4. 1/2 of 1 is 1/2 minus 4 is negative 3.5, right? Is that cool? I'm just plugging values of t in. That's all I'm doing. If I plug a 0 in here, I get negative 4. Sine of pi over 2 is 1 times 4 is 4. 1/2 of 1 minus 4 is negative 3.5. 1/2 of 4 minus 4 is negative 2. Right? Is this cool? I'm going a little fast, but I mean, I'm just plugging shit in like we've been doing this whole time. Sine of 3 pi over 2 is negative 1 times 4 is negative 4. 1/2 of 9 is 4.5 minus 4 is 0.5. Put 4 in, I get 16. 1/2 of 16 is 8 minus 4 is 4. Oh shit. So now I got a whole bunch of points to plot. Let me do this so my brain looks at it correctly. These are all points that I can now plot. And I can indicate direction that I'm moving. So 0, 4. So we're just going to use a one scale here. 0, 4. 4, 0.5. Is that cool? 4, 1/2. 0, negative 2. Let me kind of keep track of what's going on here. So I'm going this direction. Let me put a little arrow so I can keep track of what's going on. Negative 4, negative 3.5. Negative 4, negative 3.5. Negative 3.5 there. Going this way still. Is that cool? Let me just stop for a minute. So the one extra thing parametric equations do is you have to keep track of which direction you're moving, right? But I'm just plotting points here, right? 0, negative 4. So now it turns the corner and goes there. And it basically redoes everything. 4, negative 3.5. 0, negative 2. So it's back here again. Oops. Put a little arrow. Negative 4, negative 0.5. So now it's there. Look at this funky ass shape we have created. 0, 4. So now it's back up there. All right, look at that. Would you look at that? That is funky as shit. It kind of looks like a spade, maybe, if I would have drawn it better. how can I make my calculator do this for me? I don't know. Do you guys understand what just happened? It wasn't that difficult. I didn't have to know ahead of time what shape this was going to take on. I plot a point, I plot the next point, I connect them, and I put a little arrow. I plot the next point, I connect them, I put a little arrow, and I just keep going. And this is what I mean. Do you see how much freedom we have now? There ain't no function we looked at ever that would come up with that picture, correct? But now that I can control X and Y directly, I can do all kinds of weird shit. This isn't even weird yet. So if I look back at my calculator real quick, where did I go to enable it to be able to handle, what do you call it? Polar. You guys remember? What button did I push to make it go to polar? Mode. So I've already done it. So to come down to here, you put it parametric. It's crazy. So now when you hit y equals, you're going to see x of t and y of t. So you're going to have an x as a function of t and a y as a function of t. And now your variable button is going to give you t's. So I went ahead and put x in here, and I put y in there. So if you want to take a minute, go ahead and put the functions in there, right? I just made 1/2 0.5 there to make it easier. So these are the two functions that I gave you on problem number 1. One thing that you're really not used to having to do, I'll show you right now. If I go to window, what is t supposed to go between for this problem? -4 to 4. So if I go to window, I better make sure my t min is -4 and my t max is 4, right? You guys see that? Is it pretty cool? Let's go ahead, everybody make your t step. Let's all make it 0.1. That should be good enough. So let's see what happens. Let's graph this thing. Here we go. I hit graph. Shlabam. That's basically what we got, right? Isn't that crazy? Real quick, if I make the t step like 0.01, that means it's going to plot more points. The next input would be 0.01, so it's going to be more. See, it's going to take it a little longer. It's going to be nicer. So that's just what did we use for step? We used 1. -4, -3. So I'm making the calculator. I can make the calculator do it 0.0001. That's going to make it go really slow. Watch. Oh, it can't handle it. Oh, I made the... Jeff, good job, buddy. Did I do the wrong thing? No, it should be okay. Is that too far down, Jeff? Let's see. Oh, there we go. Look at that poor calculator. Working hard. Now it's plotting a lot more points, but it basically looks the same. Real quick, what if I let t go between -8 and 8? Let's see what happens. Oh man. I think this poor little dude, I'm really pushing this poor little dude. -8 to 8, let's make this 0.1 so it doesn't freak out. There we go. Look, it just keeps going up. I don't know, are you guys, normally, in the past, how would I make a collection of points? I would pick a number for x, and I'll put it in and figure out what y was. So x and y were directly related, which made my graphs have to follow certain shapes. Now that I'm using t to control x and y kind of separately, I can make the shapes do a billion different things. Holy, what? So for example, If I go back here, if I just start to play around a bit, I'm gonna take this away, take this away. What if I made this like 6 cosine of 5t, and I make this one 1 minus t to the third? I don't know. Okay, that's weird. Let me make this, let me make this t minus t third. That's even weirder. All right. What if I make this 5 sine of 2t? Neato. I mean, and again, how would I do this by hand? Exactly the way we just did it. Now, this would be probably a little much for me to give you to do by hand. Let's see what happens real quick. What if I make this 3t? It's going to become a little less busy because it's going to turn less. So that's a lot less. That's a lot less busy. Isn't that a cool freaking design? Isn't that insane? That looks like a nuclear thing, or yeah, maybe. No, not impressed. What else you got, Jeff? I don't know. I'll stop playing. I can't help myself sometimes. Look at that. That's neat. Anyway, I'll stop. Sorry. So obviously, I'm never going to give you that to graph by hand, right? Because otherwise, your brain will end up feeling like that. I don't blame it. But I'll give you some basic stuff. And again, just like the one we did, even that, it was really simple. It was 2 little equations, nothing looked weird, and it ended up with this funky-ass thing we've never seen before. You've never seen that come out of an equation before. I know you haven't. Kind of cool. Okay. This, by the way, is how you program a computer to create things, right? This is one way you can, when they program fonts, the font, the different Helvetica and all the other Comic Sans and all the fonts, the little letters are controlled by parametric equations. They kind of put them together. They could be. They don't necessarily have to be. Okay. Anyway, all right. Let me see. Yes, this guy is a little less interesting, but it would work exactly the same way. Yeah, let's try this out. I can't remember what this looks like. Let's do this real quick. So I'm only going from -1 to 3 this time. Oops, am I even showing you? No, I'm not. I love you guys. You're all like, how long is it going to take you to notice? Okay, this guy. So let's just do this real quick. If I put a -1 in, I get -1 minus 3. So that's -4. And I get -2 minus 3 is -5. Is that cool? If I put a 0 in, that's awesome. I get 0 and I get -3. If I put a 1 in, I get 1 minus 3 is -2. 2 minus 3 is -1. If I put a 2 in, I get 8 minus 3 times 4. I get 8 minus 12 is -4. Here I get 4 minus 3 is 1. Put a 3 in, I get 27 minus 27 is 0. And here I get 6 minus 3 is 3. Okay. And again, I'll do this for myself. So my brain sees what the points are. Okay. So, I mean, do you guys understand? The fundamental thing happening is I just have this variable t, and I'm still just putting shit in. So in terms of the computations we're doing, nothing's new. We've been doing that this entire time. Give me a number, let me put it in. Give me a number, let me put it in. That hasn't changed. Just the fact that that one letter controls both other variables, that's new. That's not something we're used to. And we're really not used to what kind of shapes could come out of this, right? So let's see what kind of weird stuff we get here. -4, -5, 0, -3. So now I'm going this way. -2, -1. So now I'm turning the corner here. -4, 1. You can do it, Jeff. So now I'm going this way. 0, 3. 2. Okay, that is nifty. That looks like a graffiti S or something, right? Somebody tagged my worksheet. Damn you kids. No? Yes, maybe. Do you see what I just did? Whenever I plot the next point, I connect them, put a little arrow. So whatever particle this is, that's how it's moving. Okay. How do I do, now here's where the real work comes in. How do I eliminate the parameter? How do I get rid of the t? What's really funny to me is we're about to do systems of equations, and basically that's what this is. This is a system of equations. If I want to get rid of something, I do it subversively. I replace it, right? So which equation, x or y, is it easier to solve for t? Y. What do you get when you solve that for t? Let's see. If I take this and I solve for t, add 3 and divide by 2, right? Is that cool? Add 3, divide by 2. So then this I can shove into this guy. So then I get x equals t cubed minus 3 times t squared. And I'm not going to make you multiply that out, but good if you wanted to. By the way, is this a function? Is this a function? Nope, it doesn't pass the vertical line test, right? But is it a function if I look at it like that? All day long, right? See how it's x as a function of y, not y as a function of x. That's why it works the other way. Yeah. Sorry? The line's curved?
The line has to be curved.
Oh, no. They will be curvy if at least one of your variables isn't linear. So this guy wasn't linear. That's why I knew when I connected it should be curving, right? You might not know exactly like if it's curving this way or that way, but I kind of knew where I was going, so I could guess as to which curvature it probably should have, right? Okay. But if you get the curvature wrong, I'm not going to take points off because we don't know that much yet. We don't know how to tell which way it's supposed to be curving. So if you would connected these like this, you should realize, well, that's wrong when it has to go back that way, right? But, you know, I'm going to give you some definite leeway. Everybody try to do this one. Everybody should be set in parametric now, right? Try to do that in the old graphing calculator. Let's see what that looks like. Should be nice and funky. Oh, okay. Nifty. I even forgot what it was. What shape do you guys get? Someone got that up on your screen? Yeah, you get an oval, right, or an ellipse. The weird thing is, something that's really hard to do in XY coordinates is to make it diagonal, right? That is silly difficult to do in XY coordinates. Why would you think an ellipse is easier with parametric? Well, because it's just easier to make X and Y do what you want it to do when you can control each of them directly. Maybe. Do you think an elliptical equation would look good in polar? Yeah, because it's kind of circular in a way, right? So elliptical ones are easier to do in polar. So why do we have these multiple ways of defining points in a plane? Because some problems will be easier if I do it one of these three ways. Are there other things? Oh, hell yeah, guys. I could sit down and come up with probably 53 different coordinate systems that would be useful in different situations. The one we use the most is the XY plane. But now you're starting to understand that's not the only freaking way to do it. And in fact, some problems are stupid difficult with XY, but are really easy in polar or parametric. That's one big reason why they exist. We want to solve problems, and I would like to do it easily, thank you. So, okay, maybe? Okay. So, last thing for today. This feels like we're doing a lot, but 10.6 is basically focused on doing this kind of thing. Oh shit, and a half. 10.6 is focused on the equations themselves. 10.7 is creating the graphs. Yes? Okay, and I think I was going to try to, is that part of what I'm working on? Let me see. Yes, I might, well, if you want to get ahead, go for it. I'm probably going to cut down 10.6, 10.7 homework a bit just to make it easier for us all to kind of keep up. Yeah? But if you want to go ahead and do it, you'll end up doing a little bit more, but what the hell? Okay, maybe. So this is new, this is weird, but it is not hard. Does anyone agree with me? I mean, this isn't difficult. It is new, and the graphs I get are very different from any we've seen before. But the actual work that goes into it isn't crazy. There's not a trillion steps. Okay, maybe. And there's a way to check yourself. You can just put it in the calculator and check yourself. That's crazy. All right. So, the last thing I want to do, if you look on the other side of this paper, you'll see systems of three variables. So, before we jump into that, I know, today is jam-packed, I know. Let's just talk about systems of equations. Let's see what you guys remember. Wow. Might be the best I've written in a while, and that really looks gross, but too bad. Okay. Systems of equations. So what the hell is that? It's this idea. If I give you one equation like x plus y equals 11. Let me ask you a semi-weird question. How many answers are there to that equation? Say again? Infinite. Can somebody give me one answer? What does an answer look like to that equation?
10 plus 1.
Say again?
10 plus 1.
Yeah, okay. The answer would be 10, 1. Yes? What about 110? Does that work? Give me another answer. Somebody else. 5 and 6. Holy shit, right? 9 and 2, I think you're saying, right? Somebody give me an answer with a negative number. Negative 1 and 12, exactly. Blah, 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 right? So that would take me forever. Correct? And again, remember, that's one reason why we graph lines, is because if somebody said, give me all the answers to this, and we're like, I'm not going to list them for you, I'm going to Graph the damn thing. Right? Blah, blah, blah. Do it better, but still. Are you guys semi with me? Why is that graph going down, by the way? Because if I subtract x, can't I see the slope is -1? And the y-intercept is 11? Okay, so the problem, if I said solve this, you should look at me like I'm crazy because you can't solve it. There's a million answers. There's an infinite number of answers. What if I also tell you? What if I also tell you that y minus x is 1? Now that system has one answer. There's only one point that does both things. And it's actually one of the points that you guys gave me. Look at the points you guys gave me. Which one? They all add to be 11, correct? So they all do this. Which is the only one that does this? Oh, wait, it's not a point you gave me. Damn it. Let's make this, no, it is a point you gave me. Okay, good. I was looking at it backwards. Yeah, this one, right? You guys with me? A little bit? No? Screw you, Jeff. Okay. So this is a little bit of a review. Is this familiar to anybody, this idea? So there's multiple ways to solve this. One way to solve this is graphically. If I graph this on top of this, guess where they're going to meet? They're going to meet at the point 5, 6. Why does that make sense? Because a line is all the answers to that equation. So if I do another line, that's all the answers to that equation. So what's the thing that works in both equations? The one point they agree on, the one place they meet. Okay. So what does an answer to a system of equations look like? A point. Because it has to have an x piece and a y piece, correct? Okay. Does every system of equations have to have an answer? Does every two lines have to meet? What kind of lines wouldn't meet? Parallel lines. If I have two parallel lines, there's no answer. Could there be infinite answers? Yes. What if I gave you two of the same line? Where do they meet? Everywhere. So there's an infinite number of answers then. Okay, maybe. So for example, if I said I'm twice as old as Riley, and then I say Riley is half as old as me, did I really just give you two pieces of information? Didn't I just say the same thing twice? You guys with me? Okay. Plus is probably not true. Probably 2.5 times. Okay. So one way to do it is graphically. Graphically sucks because the answer to a system of equations could be 4.378, comma, negative 11.9276. Am I going to get that graphically? Especially not the way I graph. I'm not going to get that precise of an answer. So there has to be an algebraic way to do this. Does anyone remember the algebraic way to solve a system?
Answer for
I think you said plus?
you said the
Say again?
you said the
Substitution? Is that what you're saying? Somebody? Sorry?
For y, and then put it in another equation.
Yeah, okay. So, all right, I'm going to get both of those. One way to do this, if I solve the second equation for y, what do I get? So I add x. Y is x plus 1. Is that cool? So when I ask you what is y, you don't say you don't know. What do you say? What is y? X plus 1. We know that. It's kind of another way to say we don't know, but we know it's x plus 1. So how can I rewrite number 1? X plus y, what's y? X plus 1. Why is that equation better than it was? Why is that equation better? How many variables are in this? 1. So I can solve it. 2x subtract 1 equals 10. X is 5. Holy shit, of course x is 5. We already knew x was 5. So the algebra better freaking say x is 5. How would I figure out what y is? Isn't y x plus 1? Right? So x is 5. So y is 5 plus 1 is 6. And of course, we already knew it was 5, 6, right? You guys with me? And then another way to do this is elimination. So this is called substitution, which should make sense because we're just solving for a letter and then substituting it in, right? Where did it go? X plus 1. Where did I get that from? Oh, yeah. Okay. We just substituted that in, correct? So that's called a substitution method. Elimination method is my favorite because I enjoy killing things in math, not in life, so don't turn me into the authorities. But in mathematics, it's kind of nice to kill things. Sorry, that's evil. It's just that. So, here's something that's really weird. If you've never done this before, I'm allowed to add equations together. You guys know that? If I add these equations together, what happens? The x's cancel. Do you see that? Y plus y is 2y. X minus x is 0. 11 plus 1 is 12. Now, real quick. Are any of you concerned why the hell I'm allowed to do that? Why am I allowed to just add two equations together? Are any of you concerned, or are you like, all of this doesn't make any sense, so what the hell? Why not one more thing?
Because they have like terms.
They have the same variable.
Don't I have to add the same thing to both sides of an equation? So if I add 1 to 11 to get 12, aren't I supposed to add 1 to the other side? Right? Don't I have to do the same thing to both sides? But what is 1? Isn't 1 equal to this? Bam. So if I add 1 to this side, I add 1. Y minus x is 1 to that side. That's why I'm allowed to just add two equations. Does that lead to the right answer? So far. Isn't y supposed to be 6? And then how do I figure out what x is? Well, I just pick up one thing and I put 6 in for y. And I get x is 5. Again, right? Okay. So, let's see what time it is. Let's do one. I have time for one example. Yes. Okay. Oh, real quick. One more thing about elimination. Yeah, I'll do one more elimination example, I think, and then we'll have to call it a day. What if I had 4x minus 3y equals, I should make something that works. You want something that works? Yeah, we should probably do something. If I add those equations together, does anything good happen? What does good mean? Good means I kill one of the variables, because the whole problem is there's too many damn variables. If I add those together, does any variable die? Damn variables. But aren't I allowed to multiply both sides of an equation by anything I want to except 0? So couldn't I take number 2 and multiply it by, what would I multiply it by so these would cancel? What do I wish was here?
-4.
-4. So I'm going to multiply this equation by -2. Both sides. Completely legal. Yes? Before today, there's never been a reason to multiply this by -2. Like, why would you do that shit? Doesn't do anything. But now it totally makes sense. If I multiply this by -2, I get -4x minus 10y equals -18. All right, Blue, you're not working for me. So then if I bring 1 back down, this is 2. If I bring 1 back down, can I add those together? And something good happens. Yes, right? Now those die. Good. Damn x's. What do I get here? Negative 13y equals? Negative 13. So y is? 1. Right, negatives cancel, right? And if I know one variable, I can pick either equation to figure out the other one. This is just sitting there easier. So now if I put a 1 in, I can solve for x. I went up that time, is that cool? 4x minus 3 is 5, add the 3, divide by 4, I get x is 2. So the answer is 2, 1. Is that cool? Let me ask you this. If I graph that line and I graph that line, where do they meet? 2, 1. The answer to a system of equations is always the point where these two things meet. All right. Last thing for today. I'm serious this time. Watch this. What? Oh, Jeff, what are you doing? Oh, Jeff, why? No. Oh, shit. How many dimensions does this live in? When I graph it, how many dimensions do I need? Yeah, 2, right? In an x dimension and a y dimension. How many dimensions does this guy live in? 3, which shouldn't freak us out because we live in 3, thankfully, right? So we're not all like flat. So somebody's there, I can't get around them. Oh shit. All right, sorry. This, believe it or not, that is the equation of a plane. It's the equation of a plane. So it could be, do you all agree that that wall is like a plane? Right? What's a plane? P-L-A-N-E, not plane, but like the XY plane. Right? We've said that before. If I have, how many letters are in that? How many unknowns? 3. So how much information do I need to solve it? 3. I've given us 1 so far. So let's say that is that plane. Let's say this is the ceiling. That's the ceiling. Isn't that a plane? And let's say this one is this plane. Right? That wall, ceiling, this plane. Where do they meet? Where does the ceiling, that wall, and this, where do they meet? I love how your eyes are going to the right place. Yes? Yes, where? That corner, right there, right? Isn't that point right there, isn't that where they meet? That would be the answer. And what dimension does it live in? So how many pieces will that point have? 1, 2, 3. X, Y, Z. Why, Jeff? Why are we doing this? Because we are. So this side of the paper, do you see how it gives us wall, ceiling, other wall? And eventually, I get a point in 3 space, a point in 3 dimensions. X, Y, Z. And real quick, what is a point in 3 space? Well, a point in 2 space, here's a point in 2 space, right? A point in 3 space, the Z component would be up and down. So this is a point in 3 space, so 2 space, point in 3 space would just be here. X, Y, Z, right? Or behind me, if it's a negative Z. Are you guys kind of with me? Okay. We're not going to suddenly start graphing things in 3 dimensions. Don't freak out, because that's not the easiest thing to do. If you make it to Calc 3, anybody going to go to Calc 3? Then you would have to graph stuff in 3 dimensions, which is always exciting. But I think that's plenty. Sorry, that's plenty. So tomorrow I have the updated homework sheet. Look for it on Canvas before that if you want to. Yes. Okay. And tomorrow, hopefully, I get this grade sheet summaries done. I haven't had the time. I do have more graded stuff. Some old stuff. Alright.